Something important to note about SN2 mechanisms, if you're dealing with a chiral carbon, you will end up with a configuration that goes from R to S or S to R, right? You're going to get an inversion of configuration, and that has a lot to do with how the mechanism proceeds. It's a one-step concerted reaction, so bromine is leaving right here, and while bromine is leaving, then the sulfhydric group actually, so we have the carbon sort of leaving here, and we will have the HS group coming through here. And because we have sort of like a backside type attack, then you get that inversion. Nucleophile attack from the backside. Electron density repels the attacking nucleophile from the front side. The nucleophile must approach the backside to allow electrons to flow from the HOMO to the LUMO. And this is what it looks like from the point of view of the electron orbital. So this is becoming empty, and then this is sort of being occupied by your new substituent, your nucleophile. Less sterically hindered electrophiles react more readily under SN2 conditions. In other words, if you have space for this two-step concerted process to happen, then it happens easier. But the more bulky, the more let's say sterically hindered the process becomes, then the less reactive the species become. You usually just go through a different mechanism, such as an SN1. Alkyl groups branching from the alpha and beta carbons hinder the backside attack of the nucleophile. They get in the way. This results in a slower rate of reaction. And for that, we look at the energy diagram. When you have an energy diagram, that activation energy, that barrier, is what allows you to sort of figure out how much energy you need to go from reactant to product. It also tells you a little bit about what we call the transition state, which in this case is your halogen carbon bond partially broken, your carbon nucleophile bond partially formed, right? This isn't something that that we see as a stable entity. Is something that happens in what we call a transition state to two partial bonds, one forming, one breaking. And that's, as you can imagine, super unstable, super high energy. The higher energy you need for this transition state to happen, then the slower the reaction ends up proceeding. Here we can see the energy activation energy here, here, and here. The larger energy barrier would mean that it is more challenging and it is slower for the reaction to happen. So the simplest reaction would be here, lowest activation energy. The largest activation energy means that the reaction, if it takes place, it'll be very slow and very challenging. Usually, tertiary alkyl halides don't react via SN2 mechanisms. Some nucleophiles for you to familiarize yourself with. We have strong, we have weak nucleophiles. Strong nucleophiles, you can see them here. They tend to be small, concentrated, negatively charged species, whereas here you have neutral, although highly polar species. These are unlikely to do backside attacks, they're weak, and then suitable for backside attack, small, highly negatively charged species. In general, anions are strong nucleophiles, like we just saw. Polarizable atoms are good nucleophiles. And one thing that we will see towards the end of the chapter is the solvent effect. Solvent does have an effect on nucleophilicity. Now let's talk a little bit about elimination mechanisms, specifically E2. E2 is also a concerted. The number 2 also stands for bimolecular, two species involved in that one-step process. When an alkyl halide is treated with a strong base, think about sodium hydroxide, potassium hydroxide for instance, it can undergo beta elimination. Beta refers to the position of the carbon involved in this elimination, so alpha, beta, so 1,2 elimination, it's also known as a 1,2, and you get your double bond, you get your alkene. That's the product of your elimination process. A strong base will react in a concerted mechanism called E2 elimination. So the base sort of attacks your proton donates that pair of electrons, and then the halogen of the alkyl halide leaves. You need for all of this to happen so that you have enough electrons to form that double bond, and carbon to not have 5 bonds. E2 elimination is concerted, like we just saw, where the base removes a beta proton, causing the loss of the leaving group and the formation of the carbon-carbon double bond. So conserved elimination is bimolecular because it involves two species and follows what we call second order kinetics. So first order involves one species, elevated to the one, second order, one. So 1 plus 1, that will be 2. Now a couple of general observations. When we have uh, the formation of a cis isomer, that's going to be a little bit less stable. It's going to be slower if it does happen than a trans isomer. And the reason is, as you can see right here on that electron density map, um, there is a lot of steric strain. So this isn't really favorable. This, where everybody's sort of out of each other's way, is a lot more favorable in terms of formation of alkenes. Alkyl group stabilizes carbon-carbon double bond pi bond via hyperconjugation. So that means that the higher the substitution, more alkyl groups, more stable the alkene, more places to sort of spread out that electron cloud. It is common for a substrate to have more than one beta carbon that can be deprotonated by a strong base. And so E2 elimination results in more than one alkene product. In this example, when ethoxide is used as a strong base, 2-methyl-2-bromobutane gives two E2 products. We have them right here. We have what we call the CHEM product, which will be your majority product, and your Hoffman, which will be your minority. And the more stable alkene, in other words, the CHEM product produces the major, and the less substituted will be the minor or the least stable. Now that happens because you have an beta carbon here, you have another one here, and here. These last two are equivalent to each other, so when your reaction happens through these beta carbons, then you get the Hoffman product. When it happens through this beta carbon, then you get the CHEM product. And again, it's just a matter of stability more than anything else. E2 elimination is a regioselective reaction. In other words, it favors one site versus another. When constitutional isomers are formed as the product of a reaction, with one of them as a major product, the reaction is said to be regioselective. The regioselectivity of an E2 reaction can be controlled by carefully choosing the strong base used. In other words, if I want something other than the CHEM product, then I gotta deal with this guy right here. I gotta choose a different strong base for the reaction. Experimental data indicates that a bulky, sterically hindered base will favor the formation of a Hoffman product, but an unhindered base, like the ethoxide we just saw, will favor the CHEM product. We have some percentages here. This is actually very important because in many of the questions you will see on your homework and on the test, you will get a reaction like this one. You have an alkyl halide and you get products. And based on this scenario, based on which of the bases you're using, I will ask, what is the main product? So if you're using something unhindered, like ethoxide, I would expect this to be the main product. But if you're using something very bulky, then I would expect the Hoffman to be the main product. Why does a sterically hindered base favor a Hoffman product? Sterically hindered bases, also called non-nucleophilic bases, are useful in many reactions. Here, for instance, we have a few of these. And typically what ends up happening is that the energetics of the reaction, the activation energy, changes when you go from bulky to non-bulky. Let's take a look at it here. Consider the dehydrohalogenation of a 3-bromopentane, where two isomers are possible products. We will have the more substituted, the least substituted, in this case transposition to each other, the substituent, versus cisposition to each other. Trans, less steric hindrance, cis, more steric hindrance, so I would expect this to be more difficult because of that steric hindrance, and you can see that from the activation energy required is actually higher. The higher the activation energy, the least likely and to the smaller extent that your product will form. In the alkyl halide below, there is only one beta hydrogen to be removed for E2 elimination to happen. You might imagine that it would be possible to form both E and Z alkene products, but in this case only the E alkene is product. Why is that? Well, if you look at the products, let's say you drew both, and then figure out which one is most likely to form. Here, looking at this is a phenol group. That means that you have an aromatic system. This is a terbutyl group, highly bulky. So these two, you want them to be trans from each other, opposite planes. That makes for as little steric hindrance as possible. Whereas here, they're both in the same plane. A lot of steric hindrance not really likely to happen. So I would expect the Z product to not have any significant amount formed. I would expect the E, on the other hand, to be formed. To rationalize stereospecificity of the reaction, consider the transition state of the reaction, which is something we see at the maximum of that energy diagram. In the transition state, in this specific case, carbon hydrogen and carbon bromide are breaking must be rotated in the same plane as the pi bond that is forming. In other words, these two need to be in the same plane for this whole process to happen. In other words, the beta hydrogen and the leaving group must be coplanar. Now, this makes a lot more sense when you're looking at it from the point of view of your Newman projections. In a Newman projection, you see the bromide here, you see the hydrogen here. This is what we call anti-coplanar, so same plane, but one is up, the other one is down. As opposed to syn coplanar, same plane, both of them up or down. Now, when this happens, it is a lot easier for the reaction to take place, right? For that hydrogen to leave if it's an opposite side to that bromide, than if it's on the same side. So anti-coplanar will be more favored. The staggered rotamer, where the beta hydrogen and the leaving group are anti-coplanar, is much lower energy than the eclipsed. The consequence of that is that the product resulting from the anti-coplanar rotamer is formed. So based on that, we can start making predictions as to what type of product we will get, whether E or Z, when it comes to elimination reactions. Evidence suggests that a strict 180 degrees angle is not necessary for E2 mechanisms, and it's not realistic, right? These things are constantly rotating, so for you to catch it at exactly 180, it's not a realistic expectation. So something within, let's say, that window 175, 179, 182, 83 or so, they're sufficient, right? So instead of saying anti-coplanar, we say anti-periplanar, to account for slight deviations in that coplanarity. In other words, to make it real. Although the E isomer is usually more stable because it is less sterically hindered, the requirement for an anti-periplanar transition state can often lead to the less stable Z isomer. So in this case, I would advise that you check everything on a case-by-case basis and make sure that the anti-periplanar regioselectivity is always favored.